Hey guys, welcome to our second of two parts of the combo of 8.1 and 8.2. Today we're going to be doing more review from Algebra 1. We're going to be looking at exponential growth and decay as well as compound interest. So take a moment to set up your note sheet, and then as soon as you're ready, resume the video and we will get started. All right, so we're going to start with a review of exponential growth and decay and where that comes from. So imagine that you have a website, and this website, you run this website, and in 2010 you had 500,000 members, which is okay, but certainly you're hoping for a lot more growth over time. And you're noticing that your website consistently increases its membership by 15% per year. So our goal is to write an exponential growth function that represents the website membership in T years after 2010, and then determine how many members there were in 2018 based on our model, because then we could verify if our model is actually working properly so that we could predict future membership. So if we were to make a table of values, in year 0, we would start with 500,000 members. And then our membership is growing by 15% per year. So you could think about, okay, what would I do to get to the next value? And you might multiply 500,000 by 0.15 and then add that amount to 500,000. Or if you're really thinking about it, you might say, well, I could take my 500,000 and multiply it by 1.15, which would give my original amount, the 500,000, and then 15% more. And if I did that, I would end up at 575,000. That's 15% growth in 1 year. And then I could do that again. I could multiply that by 1.15, and I would end up at 661,250. And you can see that my website's use is growing pretty quickly over time. And I could keep doing this over and over again. And that is one way that I could determine future membership, but it's very slow, because especially if I wanted to know, membership 20 years from now, this would be a very tedious exercise. So instead, what I'm going to do is try to come up with an equation to model this. And what I might notice here is that when I go to model this, I would say, well, my starting value is 500,000. I know if I think about exponential functions that the starting value is the y-intercept, so I'd have 500,000. And then each time, my multiplier to get from value to value was 1.15 every time. So my common ratio or multiplier was 1.15. And then I'm going to raise this to the t rather than x because we're talking about time. So this would be an exponential function that would model this situation. I could use this exponential function to predict, say, my membership in 2018 simply by plugging in the number of years since 2010. So I could plug 8 in here and pretty easily predict my membership in 2018. So this is the basis for exponential growth functions. They are just a special type of an exponential function. And an exponential growth function specifically has a few different pieces. You've got your final amount y, which is equal to your initial amount a, and then we're going to multiply that by 1 plus r, where r is your rate of growth. And it's really important to remember that your rate of growth is always expressed as a decimal. T is time, and that 1 plus r, that's called the growth factor. And oftentimes, we jump directly there. We just did that on the last example at the 1.15. That was our growth factor. So exponential decay uses the exact same situation. The only difference is since we're decaying, we start with our original amount, in other words, a times 1, but now we are subtracting r, where r is our rate of decay. It's important to note that r is not the amount left. It's the amount that decayed each year. 1 minus r, your decay factor, that's the amount that you actually have left. So if you're decaying by 25% per year, that means you're left with 75% of what you had the year before each year. So let's look at an example of this. Imagine that you wanted to buy a new car, and specifically you wanted to buy the newest model of the Ford Explorer. But you also know that at some point you're going to sell this car, and you want to be able to predict how much it'll be worth at that time. Because cars depreciate, or in other words, decrease in value at different rates. And that's an important factor to consider when you're buying a car, especially if you're buying a new car. So there's a company called the Kelley Blue Book, which used to actually be a blue book, but is now mostly online, that will tell you used car information. And according to the Kelley Blue Book, a Ford Explorer loses 12% of its value each year and has a starting cost of $31,600. So we want to write an exponential decay function for this, and then let's say we wanted to predict the value of the car 8 years later. So our exponential decay function would be y equals the starting amount, the initial cost, 31,600, multiplied by 1 minus the decay rate or depreciation rate of 0.12 raised to the t. So this would be our exponential decay function. And we could simplify this to y equals 31,600 multiplied by 0.88 to the t. So the 0.88 here, that's our decay factor. That's representing how much of the value is left every year compared to the previous year. So we're retaining 88% of our value each year. So if we want to predict our value in 2029, 2029 is 8 years from 2021. So we're going to put in 8 for t. And when we do that, we end up with y equals 31,600 multiplied by 0.88 to the 8, which is about $11,364.45 So this is really good to know, because if you're thinking to yourself, okay, I'm going to sell this car in about 8 years, it's good to know that you're going to lose about $20,000 worth of its value. And as I said before, some cars and some car companies depreciate much faster than others, so it's an important factor to consider when you're buying a car. And it's a pretty easy calculation to run. So finally, our last topic for this section is we need to look at compound interest. Because in Algebra 1, we did some pretty simple interest calculations. We said, okay, you borrow $12,000 from the bank to buy a car, and they charge you a simple interest rate of 4% per year. And you want to know how much you would owe the bank if you repaid the loan 5 years later. That's all well and good. The only problem is banks don't do this. Instead, banks use a mechanism called compound interest. And what that means is the bank is recalculating how much money you owe them throughout the course of the year. And as they do that, they charge you interest not just on the original rate, but also on the interest that is already accumulated, which is why it's called compound interest, because the amount of interest that has accumulated is compounding or increasing over time. And our compound interest formula is y equals p times 1 plus r over n raised to the nt, where p is your principal, or your starting amount, r is your interest rate as a decimal, t is time, and n is the number of times the bank or whoever is in charge of this is recalculating or compounding your amount owed each year. So interest might be compounded monthly or daily or quarterly or annually. Or one thing we're going to look at later this chapter is when they compound interest continuously. So just as a simple example to make sure we remember how to do this, let's look at that car loan again. And this time we're going to say, okay, a more realistic case would be you borrow $12,000 from the bank to buy a car. The bank charges monthly compound interest at an interest rate of 4%. We want to know how much we will owe the bank in 5 years. So to do that, we would just plug our information into our formula. So our principal is $12,000. We're going to multiply that by 1 plus the interest rate is a decimal. We're compounding monthly. So we're going to divide it by 12. because that is essentially giving you your monthly interest rate. But if we're going to divide by 12, that means we need to raise t to 12 times the number of years, 5, to essentially say, okay, we're doing this at a monthly interest rate over 60 months. And if you plug that into your calculator, you'll find that in 5 years, we would owe the bank about $14,651.96. So in other words, we are going to owe the bank an extra $2,651 for the privilege of them loaning us the money to buy the car. So this is kind of how banks make money. It's also how you can access larger amounts of money than you might initially have in order to make large purchases. Compound interest can also work in your favor, though, if you're the one loaning money. For example, if you're participating in the stock market, which is effectively loaning money to companies, then you can get a compound rate of return. So that brings us to the end of our video for 8.1-2b. So again, your homework is going to come from both sections, 8.1 and 8.2. So be careful when you're looking at the assignment sheet.